Hi, today we'll be discussing the frequent algorithm. A generalization of the famous Boyer-Moore voting algorithm. It was rediscovered by Demaine, Lopez-Ortiz, and Munro in 2002, more than 20 years after it had been originally presented by Misra and Gries. Let us first define the problem. Let a data stream be represented by the sequence S. Our goal is to find the elements that occur more than n over k plus 1 times. This is also known as finding the heavy hitters. The catch is in our model. We have limited memory and we can only make one pass through the elements of the stream. The beauty of the algorithm is in its simplicity, and it works as follows. If the element is not in any bucket and there exists an empty bucket, place the element in the first vacant bucket and increment its count. Else, if a bucket already contains the element, increment the count of that bucket. Otherwise, if no bucket contains the element and all buckets are full, decrement the count of every bucket. The elements in the buckets at the end of the stream are our heavy hitter candidates. However, we do have some limitations. Depending on the distribution of the stream, we may have less candidates than the value of k. It is also possible to have false positives. Nevertheless, as exemplified by the blue and green elements, we can guarantee that the heavy hitters are among the candidates. Let us prove that this is always the case. Let x be an element which occurs more than n over k plus 1 times, where t denotes its count. Let us prove that x will always be a candidate at the end of the stream. Now, let f represent the number of times in which, when x is red, we do not have a bucket containing x and all of the buckets are full. This means that in each of these occurrences of x, we decrement all the counters in the buckets. Next, let I represent the number of times in which, when x is red, we either have a bucket containing x or there is an empty bucket. In each of these occurrences, x causes its own bucket to be incremented. Observe that these are the only two possibilities when x is red. Thus, we can say that t is the sum of f and I. Next, let d be the total number of times that a bucket containing x is decremented. Since a counter can only be decremented at most as many times as it was incremented, we can say that d is at most I. Furthermore, if d is equal to I, that means that x is not one of our candidates since it wouldn't occupy one of the buckets at the end of the stream. In order to reach a contradiction, let us assume that this is the case. Then we substitute I for d. Then, if we multiply both sides by k plus 1, we get the following inequality. Now for the key observation. The values of d and f represent times in which the buckets are all full and are all decremented. The fact we can decrement a bucket represents that an element must have incremented the bucket in the past. Moreover, each of these buckets contain a distinct element, and we also have the new element in the stream that caused the decrements. This means that for each of these d plus f decrements, we can associate k plus 1 distinct occurrences of elements in the stream. Since there are n total elements in the stream, it must be the case that the number of these associated elements is at most n. But wait a second, this is a contradiction. This means that our assumption was wrong, and that d must be strictly less than I. This then means that the bucket containing x must be decremented less than the number of times it was incremented. Therefore, x must be a candidate at the end of the stream. Now, I have been purposely vague about the implementation details. Due to the nature of data streams, we usually have very little time to process each element. This means that the operations, such as decrementing the counter of every bucket, should ideally be done in constant time. Fortunately, Demaine et al. Provide a data structure that can achieve this for us. It consists of maintaining groups of counters, where each group is associated with a count value and are connected together by a doubly linked list. Furthermore, only the first group stores its true value. The others store the difference between their count value and the count value of the previous group. This is known as a differential encoding. Let us see how this works with the same example stream as before. We first check if the element being inserted is maintained within a counter. Typically, the counters are also stored within a hash table, so this check can be done in constant time. If the element is not in any counter and the first group has a value of 0, we can simply place the element in the first counter of the first group. We then have to remove this counter from this group, and if the next group has a differential of 1, we can place the counter there. If this is not possible, we can just create a new group with a differential of 1. If the element is already maintained, but its current group has no successor group, we can create a new group with a differential of 1 and place the counter there. If the element is already maintained, and it's the only one in its group, we can simply increment the value of the group. If when trying to move a counter, the next group has a differential greater than 1, we must first decrement the differential of the next group before creating a new group with a differential of 1 and placing the counter there. Now here's the trick. If all the counters are full and we receive an unmaintained element, we can decrement every counter by simply decrementing the first group's value. As we can see, we are left with the same candidates as before, all while only using constant time operations. That's all for today. Thanks for watching.